All right, so week number 6, part 2. So week number 6 is about magnetism. And it covers 2 chapters in the textbook, chapter 27 and chapter 28. Now, we already had part 1 of the screencast, which was on chapter 27. So this is chapter 28. Magnetic fields from moving charges. So this will be the theory of how B of X is associated with an electric current. So here's a short introduction. We've already defined B of X, the magnetic field. It exerts a force on a moving charge given by the formula Q V cross B. So if we have a magnetic field in some direction and some charge moving, let's say that direction, so here's V and here's B. The direction of the force is in the direction of V cross B. So if you use the right-hand rule, if your fingers curl from the direction of V to the direction of B, you see the force. Let's put the force in a different color here. The force will be, I guess, in that direction. It's perpendicular to the plane spanned by V and B. So it's a sideways force. Or if instead of a single charge, so this would be the case of a single charge Q, some point, you had a wire, well, then you would have moving charges within the wire. Each one of those moving charges, let's say the wire goes this way, each one of those moving charges would have a velocity v. Well, the mean velocity, the drift velocity, would be in the direction of the wire. And then again, there'd be a force on the wire, which would be integrated along the wire. Each part of the wire experiences a force. So the total force is obtained by adding up all those forces, which is an integral along the wire. All right. That defines the magnetic field. Now, what creates it? So it's a force field. What creates it? Well, I think I said this earlier. Electric currents create magnetism. So, for example, if you had a current loop with a, a counterclockwise current and a nearby clockwise current, they would repel each other because this has a dipole moment pointing to the right. This has a dipole moment pointing to the left. Those directions are given by the right-hand rule for these 2 current directions. And so dipoles pointing in opposite direction repel each other. On the other hand, if you had 2 current loops, let's say both, counterclockwise, they would be attracted to each other. And of course, that's why iron can be magnetized, because in a piece of iron, it's possible for all of the atomic magnetic moments to be aligned in the same direction. So we end up over on this side with the North Pole, over on this side with the South Pole. And now if you have 2 bar magnets, the North Poles oriented in such a way that the North Poles are close together, they would repel just like in this case. On the other hand, if you had south, north, they would attract, just like in this case. So they're magnetic dipoles, and they come from current. But there are no magnetic monopoles. There are no magnetic charges. In other words, if there's a dipole moment, it comes from a current. By the right-hand rule, if the current goes in this direction, the dipole moment goes in this direction. But what there is not is there is not a negative charge and a positive charge corresponding to a dipole moment in this direction. That's what happens in electricity, but that doesn't exist in magnetism. All right, so here's current, dipole moment. We often call that mu. And there's a magnetic field in the direction of mu. Well, in the center of the loop, it's in the direction of mu, but farther away, the magnetic field curls around the current. So here would be the magnetic field. I guess instead of calling this the dipole moment, we could just say, well, this is the magnetic field. So electric currents create magnetism. Again, magnetism is caused by electric currents. And it works in two ways. First of all, electric currents create magnetic fields. That's chapter 28. That's what we're talking about in this part 2 of the screencast. And when a charged particle moves in a magnetic field, it experiences a force perpendicular to the velocity and perpendicular to the magnetic field. The magnitude of the force is QV cross B. QV times B times the sine of the angle between V and B. That's sometimes called the Lorentz Force. So, I creates B, and B exerts a force on I. So you see, it's sort of a two-way street. Now, before going on to write down the equations for the magnetic field of a current, let me describe a brief history of the science of magnetism. Who discovered magnetism? Well, we know the answer to that in Western civilization. It was Thales of Miletus. Thales, the first Western scientist who lived in the city of Miletus in the civilization of ancient Greece. He lived 624 to 548 BC. So this is, 2.5 millennia ago. Thales observed that some iron ores were attracted or exerted attractive forces to iron objects. That was something he described to his students and his friends. That was the discovery of magnetism. Now, who named magnetism? Well, it was the English physicist William Gilbert, who wrote a large book about magnetism, everything that was known about magnetism in his day, back in the 16th century. And he coined the word magnetism after Magnesia. Magnesia was the province in western Anatolia where Thales lived, the location of the city Miletus. So Gilbert said, well, we'll name this effect, we'll name this force after Magnesia, where it was first observed. Now, moving into more modern times, Ørsted, Hans Christian Ørsted, discovered that an electric current deflects a magnetic compass needle, sort of by accident. He was giving a lecture about electric currents and about magnets, and as he was doing the demonstrations in the lecture, he noticed that if there's an electric current, there's a deflection of a nearby compass needle. That was 1820. So that shows that there's some magnetic effect relating currents and magnetism, what we now call the magnetic field. The same year, Biot and Savart measured it and wrote an equation for the magnetic field, or the magnetic force field. It's mu naught I ds cross r hat over r squared. If you have a little piece of current here of length ds, a little piece of wire, carrying a current I into one side and out of the other side, then it has an associated magnetic effect, which is the cross product between ds and r hat. If you look out at some distance, at some position r hat, so here's r hat, perpendicular to the segment of wire, there's a magnetic field in the direction ds cross r hat. And it goes like 1 over r squared. Ampere, a French scientist, the same year, did experiments and wrote equations. He was a mathematical scientist. He wrote the equation curl of B is mu naught J. It says if you have a current density, J, there'll be a magnetic field that curls around it. So if you have J in this direction, let's use a different color for the magnetic field, you'll have a magnetic field in this direction that curls around, curls back here, curls around in a loop. Or you can rewrite this differential equation as an integral rule. The circulation of the magnetic field is equal to mu naught I, where I is the amount of current going through the circuit. So in other words, if you have a circuit here and you calculate the circulation of the magnetic field around that circuit, go back to the color for current, there'll be a current there must be a current going through that circuit. And the circulation of the magnetic field around the circuit, that is to say this line integral, is equal to mu naught times the total current enclosed by the loop. Now, Faraday, some years later, but starting in the same year, 1820, designed motors and generators and invented the idea of lines of force for the magnetic effect. Motor is an example where a magnetic field is exerting a force on a current. A generator is different. A generator, but it has the same construction. In a generator, a coil of wire rotating in a magnetic field generates an electromotive force, a current. So that led to the engineering of electric motors, electric generators, what we now call electrical engineering. The final name in this history of magnetism is Maxwell. Maxwell lived a little later than Faraday. His life overlapped with Faraday, but he was a bit younger. He wrote down the field equations that we still use today, and he said the curl of B is mu naught J, just like Ampere said, but there's another term, plus mu naught epsilon naught dE dt. If there's a time-dependent force, if there's a time-dependent electric field, there must be a corresponding magnetic field. So magnetism doesn't only come from electric currents, it also comes from changes of the electric field. He called this the displacement current. Now you see we have two constants of electricity and magnetism. There's mu zero and there's epsilon zero. Epsilon zero we've seen a lot before when we were talking about electrostatics. Mu zero is the magnetic constant. These two things depend on what units you use. But you'll look up in the textbook the values of mu naught and epsilon naught. All right, so that's how the science of magnetism developed. Now let's go on to see how the magnetic field is associated with an electric current. All right, so in 1820, during a lecture on electricity and magnetism, Hans Christian Ørsted discovered that a wire carrying an electric current exerts a torque on a magnetized compass needle. So he noticed, sort of by accident, that if he had a compass, which would normally point north, but he put it near an electric current, a wire with a current in it, the compass needle would point in a different direction. It would point in a direction around the electric current. Nowadays, we think of this as the effect of the magnetic field. Of course, the Earth has a magnetic field, and so there's the Earth's magnetic field pointing this way, and the compass needle would line up with the magnetic field of the Earth, and playing more or less towards the north in most places in Europe, let's say. But if a strong electric current is near the compass, the size of the magnetic field due to the current is even larger than the size of the magnetic field due to the Earth, and so the compass needle will now line up with the current of the magnetic field. And you see how it curls around. The magnetic field curls around the current. In a direction given by the right-hand rule. If your thumb of your right hand points in the direction of the current, then your fingers curl in the direction of B, the vector. Now the electric motor is something similar but a little bit different. The electric motor says if you have a current going around a loop, so suppose you have current coming in here and coming out here, so there's a current going around this loop, and the loop is in the presence of a magnetic field. So let's use a different color for magnetic field. See, there's a magnetic field this way. Well, there'll be a force, actually a torque, on the current loop. That's not so much how the magnetic field is created. Maybe this magnetic field just comes from a bar magnet or something. But this goes back to the other kind of interaction between magnetism and current, the fact that a magnetic field exerts a force. It would be in one direction here, it would be another direction here, producing a torque. And Faraday showed how that could be used to make a motor. All right, but what we're interested in is really this part. How does current create a magnetic field? Or better yet, we should say, what's the form of the magnetic field created by a current? Well, the simplest current of all is a moving charge. Just a single charge, say charge Q, with a velocity v. That's kind of the rudimentary current, just one charge moving with a current. There's a force on that charge. And we know the force. The force is QV. Well, no, I'm not interested in the force created by the magnetic field. I'm interested in the magnetic field created by the charge. As the charge moves, it creates a magnetic field. I guess that's the way to say it. As the charge moves, it's a little tiny current. And it creates a magnetic field, as all electric currents do. And here's the magnetic field associated with a charge q moving with velocity v. It's a constant, mu naught over 4 pi. That's just a universal constant, which depends on the system of units. You can look up the value in the textbook or on Google. It's qv cross r hat over r squared, where q is the charge, v is the velocity. R hat is the length of the vector r, x minus xq. So r is the distance between the charge, or r is the vector, from the charge to the point where I'm measuring the magnetic field. So if I have the charge here, and it's moving in this direction, so there's q, and there's its velocity. This gives you the magnetic field here at the point x, where r is the vector from q to x. So that's r. And r hat is the length of r, is the direction of r. R, plain old r, is the length of r. So this is r vector. So you have to be very careful to use vectors when you're dealing with magnetic fields. Now this formula is really only approximately correct. It's correct when the velocity v is small compared to the speed of light. Now the speed of light is very, very fast. So for all practical purposes on Earth, the speed of a moving charge would be small compared to the speed of light. Well, that's not quite true, because in charged particle accelerators, you can have particles, individual like electrons or protons, moving at about the speed of light. But for engineering purposes, particles move at speeds small compared to the speed of light. So this is a good approximation for the magnetic field produced by a moving charge. So here's an example. Here's a positive charge with a velocity in the z direction. So the velocity vector is like this. So there's the velocity vector. And then these little arrows represent the magnetic field at various points in the space around that. So that would be the electric field due to one charge. The magnetic field. Now, magnetic field, like the electric field, fills up a whole volume of space. So the magnetic field is defined every point in space around that moving charge. We could rewrite this in a simpler form using cylindrical coordinates rho, phi, and z. So if we have this is the z-axis, and this is the rho direction, and this is the phi direction, rotating around z. You sort of have to try to view this in 3 dimensions. So I guess phi would be around like this, making a plane, and z is perpendicular to the plane. So this is z, rho is out this direction. Phi is in the same plane as rho. Phi is the direction around the axis. So there would be phi around the axis. In other words, we write x as rho hat plus z k hat. So x is someplace out here. Which is a distance rho from the z-axis and then up by an amount z from the origin. I don't know, maybe the origin's down here. So this is how we write the vector x using cylindrical coordinates. It's rho hat plus z k hat. And let's again say, like in this picture, that the velocity is in the z direction, so it's v0 k hat. And let's put the charge at the origin. So let's say xq is 0. Then b will be in the azimuthal direction. So b will be b phi hat. And b phi could depend on rho, phi, and z, but in fact it only depends on rho and z. It doesn't actually depend on the angle around the z-axis. It just depends on rho and z. The direction depends on phi. The direction is the direction around the z-axis. By the equation, it's mu naught q v0. Now k hat cross rho hat, here's rho hat. K hat cross rho hat, well, the z part will be 0 because k hat cross k hat is 0. But z hat cross rho hat will be phi hat. So we'll have z rho, well, no, k hat. So it'll just be there won't be any factor of z. There'll just be v naught phi hat divided by 4 pi, and then r squared. Well, r squared from the origin to x is rho squared plus z squared. So there's one way of writing the magnetic field, which looks fairly simple, but it's simplified by the fact that I'm assuming that the charge is at the origin. Here's how I have to write the magnetic field if the charge is at some arbitrary point x sub q. All right, so make sure you're taking notes, writing down these equations, because you're going to have Lorentz problems which will involve these equations. You need to know what they are. All right, now we've seen the magnetic field created by a single charge with some velocity. Now, what's the magnetic field created by an element of current? So what we've seen is a case of a charge q moving with a velocity v. Now consider something a little different. Suppose you had a little element of a wire. So there's a little element of a wire here of length ds. And through that element of the wire, there's a current I. So the current I is coming into this end and leaving this end. Then what's the magnetic field? Make magnetic field this color. What's the magnetic field here? That's the point X. Well, if you think about it, current times ds is really the same as Q times V. Q times V is Q delta X over delta T. Velocity is distance over time. Now Q over delta T, that's current. So that's I. So it's really I times dx. Or I would say I ds. So I have the same equation, only instead of QV, I have I ds. So the magnetic field, let's say the magnetic field due to a little short segment of wire delta S, we'll call that delta B. Magnetic field at a point X, over here, is mu naught over 4 pi I ds cross r hat over r squared. If I think of just one charge moving here, the current times ds would be q times v. So I'd have qv cross r hat over r squared. Well, here, since it's a current, I have I ds cross r hat. Those are the same thing. Again, r hat is the unit vector of, in the direction of r vector, which is x minus x prime. X is the point where I'm measuring the field. X prime is the position of the little current loop. So here's x, and that point is x prime. And I really should keep track of everything that's a vector. So the vector r is just the vector from x prime to x. So r is this vector from x prime over to x. That's r. R hat is the unit vector of that length, of that direction, and r is the magnitude of that vector. So a moving charge, or an element of current, a little piece of current, they have the same form in the magnetic field that they create. Now, of course, you can't really just have an isolated little element of current. Current flows in loops. A current has to flow around a circuit. So what's the magnetic field carried by current in a wire? This is a little part of the wire, but what about the whole wire? That'll give you the whole magnetic field. Well, you just have to sum up all of these elements, and when you sum an infinite number of infinitesimals, it's an integral. So I'll have this constant mu naught over 4 pi, now the integral along the wire, this amount of current for each little portion of the wire, so I ds cross r hat over r squared, where again, r is x minus x prime. Let's do an example. Let's consider a long straight wire on the z-axis. So suppose I have a very long wire. Oops, I better use that in this color. Let me suppose I have a very long wire, and it goes down below here, all carrying current I. And I want to know what's the magnetic field at this point x. Well, I have mu naught I over 4 pi. Those are just constants. I'll have the integral. Now ds will be dz, k hat. ds is this vector. It's in the k hat direction. It's along the z-axis. So ds is the length times k hat. I have to say this is the z-axis. So ds will be k hat times the length of ds, and the length of ds is just dz. So here's k hat dz, and r hat will be this vector. R will be this vector. Well, you see, that's r, that's rho hat. It's a distance rho from the wire, perpendicular distance rho. So that will be rho hat. So if I have a factor of rho from r, and now I have k hat cross rho hat. K hat cross rho hat is phi hat. So k hat is upward, rho hat is perpendicular, phi hat will be in the azimuthal angular direction. So here's k rho phi. So I ds cross r hat, well, no, I ds cross r will be dz rho phi hat times I. I is a constant along the wire, so I can pull that outside the integral. So that's the numerator. Then I have r squared. No, I have r cubed because I changed this r hat over r squared to r vector divided by r cubed. This is r vector divided by r cubed, and the r vector has the length rho. So I have to have down here rho cubed, and rho cubed is r cubed. So r cubed is rho squared plus z squared to the 3/2 power. All right, so to go from there to there is a bit of trigonometry and algebra. So to check your understanding, see if you can get from this equation to this equation. You know, the ds was replaced by k hat dz. The r hat was replaced by rho hat. Then k cross rho hat is phi hat. But I put an r up here, so this has to be an r cubed. All right, now I have to just do the integral. But the integral, that's an elementary integral. It's z over rho squared, square root of rho squared plus z squared. So I have various constants. I mean, rho is a constant as far as z is concerned. So I have the constant mu naught I rho over 4 pi. I have the direction phi hat. That's independent of z. So I have the direction phi hat. Then I have the integral over z. And the integrand, the antiderivative is z over rho squared, square root of rho squared plus z squared. Has to have units 1 over length squared. So this will be length over length cubed. So that would be right. Now, it said it was a long straight wire, so the wire goes from minus infinity to infinity. So the endpoints here are z equals plus infinity and z equals minus infinity. Now if I set z equal plus infinity, I can neglect the rho squared here. I just have z over z. The z's cancel. I just have 1 over rho squared left. So when z is plus infinity, this quantity is 1 over rho squared. Then I have minus the value of the antiderivative at z equals minus infinity. Well, if I set z equals minus infinity, I'm going to have here z over the square root of z squared. That'll be minus 1. Z is minus infinity over the square root of z squared, so that's minus 1 over rho squared. So the value of the antiderivative at minus infinity is minus 1 over rho squared. So if 1 over rho squared minus 1 over rho squared, that's 2 over rho squared. 1 over 4 pi times 2 gives me 1 over 2 pi. Rho over rho squared is rho. I have this factor mu naught I in the direction phi hat. So here's an interesting formula. It's the magnetic field due to a long straight wire. At a point, a distance rho, that's the perpendicular distance from the wire, and the direction of the field is azimuthally circulating around the z-axis. So this point x has rho component rho and direction phi hat. So in cylindrical coordinates, that's the magnetic field of a long straight wire on the z-axis. This little computer program does the integral. You see the antiderivative comes out. Z over a squared times the square root of a squared plus z squared. Z over rho squared times the square root of rho squared plus z squared. The example of the magnetic field created by a current in a long straight wire, mu naught I over 2 pi rho phi hat, that's a very basic example. So this is something you definitely should have written down in your notebook. There'll be a bunch of line kappa problems where you have to use that magnetic field. Now, this is all based on this equation for the magnetic field due to an element of current, a little portion of current of length delta S, current I, at a point x, which is a distance r away from the current element. That's called the Biot-Savart law. That's called the Biot-Savart law, and that is an example, or the application of that, is an example of superposition with integration. You see, when I calculated the magnetic field created by a current, I took that Biot-Savart law and then I integrated over all the current elements. So that is an example of integration for a known magnetic field. That's the Biot-Savart law. Now there's another way to calculate magnetic fields, which is much easier. Doesn't involve an integral. Well, actually it does involve an integral, but it's simpler. But it doesn't always work. And that's called Ampere's law. So that's the last topic, Ampere's law. Ampere's law is based on this theorem. The circulation integral of B dot ds around a closed curve is equal to mu naught times the current I going through that curve. So the picture goes like this. I have a curve, a closed curve. We'll call that C. And I integrate the magnetic field, the tangential component of the magnetic field, around that curve. So I take a little section of the curve here, ds. I dot product with the magnetic field at that point. There's the point ds. So this is the tangential component of B in the direction of ds. And then I integrate all around the curve. That's what's called the circulation of B. It's the circulation of B around a closed curve. Well, through this curve, there are currents. So there's current going through the surface. There's current through the surface. The surface whose boundary is C. So in here is the surface. And there's current passing through that surface. The circulation of B is equal to mu naught, that magnetic constant, times the total current through the surface. In other words, I have to add up all the current through the surface. That's just a theorem. That's called Ampere's law. Now, if it's a theorem, we should be able to prove it. Well, let's prove it by one example. And prove this in general. And this is a very general theorem. It holds for any closed curve. But let's just prove it for a simple example. Let's take again a long straight wire carrying current I. Let's say that's the current that's going through the curve. And let's take the curve to be a circle. Well, let's see, let's use different colors. So let's take the curve to be a circle in the XY plane. And let's take the current to be a current on a wire along the z-axis. So here's the current. Here's the Amperian loop. It's a circle. We have to try to view this in 3 dimensions. The current is along the z-axis. So a long wire along the z-axis. And that wire carries a current I. And now I consider the circulation around on a circle in the XY plane. So let's calculate the circulation first. It's the integral B dot ds. Now B is mu naught I over 2 pi rho phi hat. So that's mu naught I over 2 pi rho phi hat. And now dot ds. Now what's ds? ds is a little length element here on the circle. That's phi rho hat d phi. So if I have a little part of this circle, let's put it in a different color so we can tell the difference. So let's say I have a little section of this ds. So there's ds. Its length is rho d phi, where phi is in radians. Remember, phi is the angle around the z-axis. So d phi is the amount of radians. Rho d phi, rho's the distance, is the length of that little arc. So there's the arc length, rho d phi, and the direction of it is the direction of the of the circle, which is phi hat. So now, phi hat dot phi hat is 1. The rho cancels the 1 over rho. Mu naught I over 2 pi, that's just a constant, because I have a constant current along the z-axis. So I have this constant, mu naught I over 2 pi times the integral d phi. And the integral goes all the way around the circle. Phi goes from 0 to 2 pi. So the integral 0 to 2 pi of d phi is 2 pi. So this integral is 2 pi. Divided by 2 pi cancels out. So the answer is just mu naught I. So the circulation on this Amperian loop is mu naught I because I goes through the loop. Now that's a simple case where I took a circle, whereas Ampere's law is true for any circuit. And I took a circle where the current goes through the center of the circle. So I took a very simple case and I verified the theorem. But in fact, the theorem is more general than the proof. So this is just a proof by one example. And a completely general proof requires some advanced calculus. Now the point is that Ampere's law can be used to derive B of x for highly symmetric systems. And there are some examples in the textbook in sections 28.3 and 28.4. So you're reading chapter 28 this week. In addition to 27, you're reading both 28 and 27. If you look at sections 3 and 4, you'll see how Ampere's law can be used to derive B of x for highly symmetric systems. Now that completes part 2 of the screencast, how to calculate the magnetic field if you're given the electric current. Now there's one more part of the screencast, which is called part 3, which will be some examples. And those examples will be somewhat similar to some of the Lorentz problems. So go on and watch part 3, and then you should be in good shape to do the Lorentz assignment.